Are we good? All right. Hi, everyone. Thanks for coming to my talk about Transformers for Math. I'm Roy. I'm just a lay member in this club, but I like this, so I'm going to talk about it. So the game plan is, we're going to give a quick thing about Transformers. Who here knows what a Transformer is? Okay. So I think I still will go through the background. And then we'll be going over arithmetic transformers as like a quick example of using them in math and how it's not as easy as it seems. And then we'll talk about priming, which is a paper in 2023, which is like pretty cool. Some cool observations on arithmetic transformers. And then we'll be going into symbolic math tasks with transformers. I think that's going to be like the meat of today. And also seeing how we can use this for open math problems like discovering Lyapunov systems. Okay, so let's attempt my poor summary of a transformer. Okay, so the transformer is basically a foundational architecture we use in the deep learning world. And in one sense, also correct me if I say anything wrong, I really appreciate it. But in one sense, we want to generate, given a sequence, we want to generate another sequence based on all the previous tokens. So we want to optimize. So we want this probability to be as accurate as possible. Professor Grigsby likes to summarize it as like a series of functions that go from um like your vocabulary space into the model space, something like that, and then some something like that, and then you output, your token here in the vocabulary space again, right? And then in between here are like the actual mechanics of the transformer itself. So let's take a look under the hood. Oh yeah, so here are the key parameters. I use this fancy T here to indicate the corpus or our vocabulary you're working with. I guess the corpus is exactly the same as vocabulary, but these are just all the terms we will be able to accept and also output. And then the main idea is that we want to take a certain input token, and kind of reduce its dimensionality to this like smaller space. And then hopefully in that case, we can represent it with like an actual semantic meaning. I might be butchering this, but in general, in that subspace, we want like the vector for something like dog to be super close to a similar word. So like a vector for dog should be similar to a vector for canine in that subspace. And then we also have the context window size. So not only do we want to reduce uh, this into a subspace so we can encode the meaning, we also want to then generate a new token based on the previous tokens in that subspace. So let's crack it out, and we see this beautiful diagram. So there's two blocks in the transformer. There's the encoder block here and the decoder block. The encoder block is the main block responsible for both. So first, this input embedding is what reduces a token to the actual model subspace. And then inside the encoder block, I like to think of it as like building the actual meaning of the subspace. So as you train it, then the vectors will be, I guess, more accurately representing the meaning of the tokens. So canine and dog will get closer together, while things very different, like maybe dog and Eiffel Tower, will get really far apart, right? That's the idea of the encoder. And then we feed that into a decoder, which takes those meanings and tries to extrapolate a new token. So the main mechanism is attention. So in a classical case of the transformer paper, they talk about using it for translation between English to I think German. So in that case, you would do cross attention. The idea is comparing how similar a word like say me and another word in different language, like, well, how close these words are together, right? And then you want to score that with attention. But in this case, we can do it to our own inputs. So for instance, with an input like, what's a short input? I think, therefore, I AM, right? We can write that twice. And then compute kind of similarity or attend to the relationship between each input and another token within its own input. Did I lose anyone yet? I'm sure I lost one in the beginning, but yeah.
The last slide.
Yeah, there's a lot going on, yeah.
What is the output?
The output embedding? Yeah, I'm fairly sure the output embedding is another learned way to take previous tokens and embed them into the model space. Someone correct me if I'm missing something extremely crucial.
There's like a input and like what's been generated so far.
Mhm.
I should have
It's like the model received this input, the prompts as well, along with everything it's given so far. I think that are keys by.
Yeah. Anyone else? All right, I'm gonna keep pushing. Okay, so we can compute I guess a score of quote unquote similarity or attend to using three weight matrices, a query, a value, and a key matrix. So we denote those Q, K, and V. So in this case, for one logic or like basically one kind of I guess like unit of attention, using these we can say we can take say like we're at this current token, we can compute X, I, W, Q as like the query, and then attend to maybe, think, then we can get X, J, W, K, and then take the scalar dot product of that. And that's kind of like a score of how similar these things are. That's like a very, I guess, high level way to see it. Because these are learned, so because the query and the key matrices are learned, then as the representations become more and more accurate, you want like different things to be on the scale of dot product closer to zero. So if you had like dog and like Eiffel Tower, then hopefully in this the scalar dot product will be closer to a small value, and if they're similar, then it'd be larger, I think. And then we want to divide it by square root of dk, where dk is the model divided by the number of heads, because in this case we can compute attention with a lot of heads at the same time, usually like 8, at least in this paper, which gives 8 different representations of attention. And this is just to help computational stability. And when you compute it for multiple heads at the same time, you end up getting multiple representations of attention, because as the model optimizes by being able to like represent like multiple attention relations, it can have more expressive capacity. So it'll end up using these multiple heads, even though they're trained on the same data, they'll have different weight matrices for queries, keys, and values. Okay, so we take this logic, and then this is the actual output of the attention layer, the multi-head attention layer. For one of them, it's this ZI. We take the softmax. Does everyone know what a softmax is? Okay, so a softmax is basically a way to convert one logic to a probability. So if you look at this logic here, we can think this is the equation. It's EIJ over some like sum K over all the E, something like this. Yeah, so you sum across all of the other logics in a column, and then this outputs like a probability between 0 and 1. So it's a way to generate a probability from this I guess like unit of attention. Okay, and then we append all of the different multi-head attention outputs together into one big matrix, and then pass it into the feed forward layer. So if you go back to here, that gets sent into here, and then we can repeat that number of times. So even though in this picture there's only I guess one encoder block, usually they're stacked up to like I mean I think in this paper they do it like 6 times, but you can stack it to gain more expressive power on paper. So any questions about the encoder? Yeah.
What is the probability?
So this I mean it's some probability between like 0 and 1. It's supposed to reflect like um I guess like it depends on like how big of a value EIJ is, so it's supposed to like reflect like how strong of a attention unit it is. But I'm not exact. I mean, I don't think anyone would know exactly like what probability this is, and like I kind of don't have like a good intuitional explanation for it. If anyone in the crowd wants to help me out, like what's a good intuitional explanation for what this probability is?
Or they use the word like it means, what do you get probability? It's mentioned.
Like, so for instance, when you do a softmax at the end there, maybe this is a better kind of example. You're classifying the decoder output into one of like your actual words in the corpus. So say you have like you work with English, right? You have like 49,000 words you're considering. Then when you take a softmax, it'll convert it to a big vector, I think 49,000 deep, and then for like the token that corresponds to that decoder vector the strongest, then it'll have the highest I guess output. So in that case, yeah, if you had like if it was a dog vector, then the outputted probability for dog would be the highest. But that's after you like run it through the whole decoder. Yeah, what's up?
Probability is like the output like a speaker. It's like how likely a probability score is based on the prompt is probably very high. So you have to choose like the most probable. Because yeah, you know, it's ChatGPT. It's like it does one thing.
Yeah.
Oh yeah, it's the most probable.
Yeah, that's not like, yeah.
I mean, but I don't have like a good explanation of like what it does in this point, because you also do it between this multi-head attention layer and the add and norm layer. So like I don't know if that example of like classifying it into an actual word is this will work in this case. So yeah.
So are you saying you're doing this?
Yeah, so at the end of each attention head, before we feed it into this other matrix called like a WO, like the output matrix, the feed forward layer, then we do a softmax. So just check out the paper, I guess maybe they might have a better explanation. But I was trying really hard not to turn this into a transformer talk because I don't think I have like a strong enough intuitional understanding of it to be really convincing. So let's move on to talking about positional embeddings, because this will be like a cool part of the talk today, hopefully. So when we think about computing the attention or attending to certain pairs of these tokens, right? So notice in this sequence, I think therefore I am, we see I twice. So without a positional encoding, then both of these I's would have the same attention matrix, I guess, or like they would have the same attention values between all the other tokens, even though these two I's represent two different meanings, right? Like I guess they both represent the person speaking, but they mean different things in this context. So to capture that kind of subtlety, in the original paper, they use absolute positional encoding by using a sinusoidal function and then adding that to the initial input embedding. So if you remember this diagram here, so after doing the initial input embedding, then they add that sinusoidal function. And the theory or the hypothesis is that a sinusoidal function, because it can be each sinusoidal function can be represented by a linear combination of other sinusoidal functions, I think. So it can maybe generalize to arbitrary length, but that's actually not the case. You see here for transformers trained to do addition, they don't generalize well to things beyond what they've been trained on. And this is the bulk of the talk, or the first half of the talk we'll get into today. So let's look at a couple other things. So here's one fix that someone tried to implement called relative positioning over keys. So the main idea is that instead of using an absolute position, we can embed two learned vectors to represent a kind of a distance between tokens, and this will help I guess like build that positional encoding. So they show up in this way. So as an extra addendum to the logic and then to the actual output itself, like that. And this is like from a Medium post. I stole this picture, but I think it's a good way to show that the actual I guess like pairwise positional vectors themselves don't depend on the value of the token, but just depend on the place. So for instance, this one represented by 5 between the second I and AM is the same one as between the first I and think. But the problem with this is it's extremely memory expensive. There's 2 times 2 to the k minus 1 learnable vectors, depending on the context length. So you'll have a huge like matrix to compute every time, even though you can flip it to be smaller. Like at a certain point, the context doesn't really like affect it that much, but it's still extremely memory expensive. So someone devised Huang and his team devised or her team devised a better iteration on it. And the main thing is that it's a lot less computationally and memory expensive, but the overall idea and I think the behavior is very similar, where they only use the key vector, so it's only like one of I think it's only this direction, and it still maintains similar results or most of the results. Okay, and then the final thing is this idea of a universal transformer. So this is basically at least in Gelasi's paper I'll be discussing soon, it's a way to integrate reattending to more ambiguous tokens. And it's also a way to add like recurrence to your transformer. But in this actual paper, they go into like way more and discuss how apparently U transformers can be like Turing complete and can act as like universal Turing machines, which is really cool. But in our case, we just want to use its expressive capability. So let's get into Gelasi and that team's paper, length generalization for arithmetic transformers. So the main problem, as we saw earlier, is that for arithmetic, transformers fail to generalize. So in this case, they were trained on addition up to 5 digits. And then we can see that with absolute positional encoding, it fails to, well, I guess it slightly generalizes for 6-digit and 6-digit addition and completely fails for anything beyond that. We'll get into more observations, but that's just the motivation for this paper. So they set up their experiment like this. They take 2 integers, positive integers, x1 and x2, and then they sample from x1 any 5-digit integer within this specific set of 5,000 integers. And then x2, they sample either a 5-digit integer for addition or a 3-digit integer for multiplication. So they do this because they want to make sure the sample size is really small to prevent overfitting, since with transformers, one of the biggest problems is they can lead to overfitting, especially when you have a limited amount of data. And then in the test set, they both test in domain. So for multiplication, that'd be like 5-digit times 3-digit tests, and also out of domain. And then when they're processing the tokens, they add padding to allow like smaller number of digits to be used with larger amounts of digits. Okay, and then in their setup, they do these 3 steps. So they embed into the model space with one of the 3 positional encoding schemes. And then they use an encoder only model, and then they linear classify to determine the actual digit outputted. So getting deeper a little into it. So the linear classifier layer, they only use the encoder, right? So they'll have like a output of vectors in the model space, and then they truncate that output to n out, which can be determined by whatever process whatever operation you're doing. So for instance, in multiplication of like n by m digits, then we know that n out is at maximum n plus m digits, right? So that's how you get n out. I'm not sure exactly what the model will do after like n out, because I don't know like what the vectors it produces after n out digits will represent, but I think they will generate zeros, but they didn't mention that in the paper. And then they just linearly classify this number of vectors to between 0 and 9 digits. What's up? Yeah. So say you have like so you have x1 times x2, and this is like 1, 2, 3, 4, 5. So it's 5 digits, and then you have another one. It's like 1, 2, 3. Then the output will have a maximum of 8 digits long. Yeah, that's it. So NL is just less than or equal to them. Well, NL is just the maximum number of digits it can output. And it's always n plus m for addition, and I think it's like what, n plus 1 for addition. And so does that make sense? Did I say addition twice? So n plus m for multiplication, n plus 1 for addition, and that's just a capped maximum. Okay. And then this is why they use universal transformers, because universal transformers are effective previously for length generalizing tasks, such as, or not, I guess not length generalizing tasks. They're effective for modular arithmetic, and then other recurrent models like an RNN is successful for length generalizing tasks, such as this paper, they talked about like training an RNN on like a 9x9 maze and then trying it on like a 64x64 maze, and it still works. So that's pretty cool. And then encoder only, because we don't actually need to generate more tokens at the end. It seems to be the main reason. And we can and for situations where I guess like for situations where you might want an encoder and decoder, it's like an added layer of complexity you don't actually need. That seems to be the main argument. Because you can just classify the encoder values into digits. But I'm not exactly too certain why it's an encoder only design. Okay, so here's their main observation. It fails for multiplication to generalize from beyond 5 digits. And then for addition, you can see RPE, both versions have some level of generalization to like 15 digits. Seems pretty successful. But once you get to 20, it still fails to be at a satisfactory level. So the main reason behind it, they ran a test so that absolute positioning they learn can't learn the operation digit by digit. It fails like element-wise addition. So that means like for something like 99 plus like 36, then if you ignore the carryovers, then this would be like 5 and this would be 2. So it like can't learn this apparently. And it has a couple of results in their appendix about that. But they were very uncertain about why RPE fails to generalize. Also, they tried fine-tuning. So this is like a version of transfer learning where they first train their model on their base task, which is 5-digit by 3-digit multiplication in this case. And then they try retraining it on 35-digit by 3-digit multiplication examples, and they find catastrophic forgetting, which means that you can see in this graph, as they train more on the second use, the first use starts to degrade in quality. So this doesn't work. So their solution, don't generalize to a certain extent. If you just inject for each general case you want to extrapolate to, if you just inject a couple examples, you improve performance substantially. And so that whole concept is called priming, injecting examples. And the amount to inject is determined by a priming rate we call like epsilon percent, which is usually like extremely tiny as it scales logarithmically with the amount of data. They found this scaling empirically. I don't think they have like a unified theorem behind it, but we can see in their results, this is extremely successful. So adding, I think this is like 50 examples to their like 1,000 example training set or something like that. They achieve successful generalization to 35 by 3-digit multiplication. And then they also note that you can only generalize to situations you've already primed. So they prime only even number of digits in this case, and it only works for even number of digits. And then priming works for both absolute positioning and relative positioning. And all cases that get primed eventually work. So this is like to me at least, like a really surprising result, because I wouldn't expect injecting so few examples, like 50 among like 1,000, or like maybe it was like 100,000 training samples to work. But it does. And this is just for arithmetic, so a lot of people are wondering about like extrapolating this to other fields. Like maybe you can use this in like a large language model if you inject like, say you want to make like a medical model, if you inject like a very specific, medical question answer pair a couple times, maybe it'll work better for those types of situations. But yeah, it's a cool phenomenon. So I hope that's like a good taste of, using transformers for math. Here are a couple other phenomenon. One of them is called grokking, which is so if you overtrain on a very small data set for like modulo addition, after like I think like 100,000 epochs or a very long time, it'll actually eventually learn rather than overfit, which is crazy. And then Francois Charton talked about, like, he didn't call it inverse grokking, but that seems to be, I don't know if that's a good name or not. But basically, if you train for another simple task like multiplication of modulo 67, a model trained on a very large data set fails to generalize, while a model trained on like a quite limited data set generalizes pretty well, which is also an open problem on like, why does this happen? Okay, so let's look at deep learning for symbolic maths. And this is basically using transformers to generate and solve integration and ordinary differential equations. So the motivation is that, I mean, we already have like systems that can solve integration and like ordinary differential equations, like Wolfram Alpha, Mathematica, all that. But usually those are search problems where they apply a set of heuristics, like, look to do integration by parts first or something, or like pattern match, like the equation, and then use that to solve. So it'll generally take a long time for very complex equations or very complex expressions. And sometimes they're not accurate. So sometimes they fail to integrate something that can actually be integrated. Yeah. Also, since we're using transformers, we can extrapolate. If we have a way to do this, we can extrapolate that to LLMs, which are pretty cool. And then with this concept, hopefully, like this method for developing integration and ODE solving, we can apply it to harder problems like open problems in math. So here's their approach. So first, they represent every expression as a tree of expressions. So for something like 2 plus 5 times like 3 plus 2, hopefully I do this right. We can represent this as a tree. Yeah. So we can break it down into a series of expressions in a tree, and then we can use postfix operation to tokenize them. So in that case, I have an example here. I don't want to get it wrong, even though this is like a CS2 question. But yeah, uh, we can tokenize it using postfix notation. So that's how you can feed this input as a sequence into a transformer. But the hard part is generating these sequences. So with a naive method, like let's just randomly generate, nodes, a series of nodes, and like randomly generate like which operators. We'll get very unequal distribution of trees. So you might get trees that are super deep or trees that are super skewed to one side, depending on your generation scheme. So we need an algorithm that's really good at finding all trees with an equal distribution, right? And the way they do that is really complicated. I don't want to get into it. I don't think I quite understand it myself. But they use a series of observations. For instance, like they've using Catalan numbers, you can find like the depth of a full tree. And then they also augment their tree because in math you have not only binary expressions like this where it takes two inputs, but also unary expressions like say cosine. Then in the tree it would look like, something like that. So cosine of 3 would look like that. So your tree is not necessarily always going to be full. You might have a lot of unary expressions instead. So based on a series of computations and a series of proofs, they find their sample space to be up to 10 to the 60, up to 10 to the 62 possible expressions when limited to only, I think, 15 internal nodes, which means like 15 of these expressions like multiplication, addition, cosine, all that. So a huge sample space. And this is my attempt at summarizing their generation algorithm. They generate, or at least try to generate like all possible trees and then sample from it randomly in a uniform manner. And then once they sample a tree, they sample it ignorant of like the actual values inside it. And then, so once they have that tree, they kind of decorate the values and the operators inside by randomly sampling the actual values, expressions, variables. And you can do that uniformly, or you can have like a preset probability distribution to do that with. And then finally, they clean those terms. So for instance, if you get an expression that's like 1 plus 1 plus 1 plus 1, you can just fold that into an actual value. And it works a lot better. Okay, so this is the coolest part to me. They have a forward generating data set, they have a backwards approach, and then they have one by integration by parts. So let's talk about the forward generating data set first. This is the most straightforward. You basically just have a random function, and then you run it through Mathematica or something to get the solution. So if you have like an integratable expression like x squared, then you can just ask Mathematica what the answer is, 2x, and then you add this pair to your training set. Pretty straightforward. The problem is this only works as well as Mathematica does. So if Mathematica is really slow, then generating this data set will take a long time. Also, for certain integratable expressions, Mathematica can't integrate them. So this is also limited in, like, I guess the scope of its sample space. So their solution, they use a backwards generating data set. So they start instead with a function f again, but instead of running it through Mathematica, they just take the derivative, and this allows you to generate a lot of pairs. But the problem is that it's unlikely to generate the integral of simple functions with long derivatives. So for derivatives with like tokens that with way more tokens than the input, like this, it's very unlikely to generate that. So they have the third approach, which is integration by parts. So basically, if f prime times g is like, if that expression is within their data set, then they can generate all the other expressions within integration by parts. So those are the three unique ideas. They have this scheme for generating ODEs, but I'm not going to get into it. I think I'm running way over time. Yeah, and then they have another one for generating second degree ordinary differential equations. Okay, so this is the data set. You can see it's huge, like 20 million, 40 million examples for each type. And then how they did their inference is they used a beam search at the end of each expression. So a beam search is basically you can score each output. They used like log something, log linear. You see log likelihood. They use log likelihood and then normalized it against the sequence output length. And then so that means if they take like the top 10 or top 50, depending on the depth of the beam search outputs. So that takes like maybe like the 50 best examples or the 50 best outputs. And then if any of those 50 outputs are valid solutions, then we consider that iteration successful. We consider that iteration accurate. And this is because according to them, it's easy to check if an output is a solution. Yeah.
Could you just talk about model for a second?
I'm actually not too familiar with log likelihood, but besides like the fact that it's a way to score these outputs. Does anyone like, can anyone give a good explanation?
Just like before you take the exponent, you want to explain what beam search is? Yes.
Okay. Sorry.
So, when you're doing predictions using transformers and you're trying to predict like what the next sequence of tokens is, transformer only gives you the probability for the next token, right? So if like I have a that it can either be cat or dog, and then after that token gets added, you can add more tokens onto it, right? And each of those tokens has a probability, and the probability of all of this happening is the product of all of those probabilities at each level. So what can happen is if you take the most likely probability at each step, that might not lead to the most probable sequence. Like being greedy will not lead to the optimal sequence in terms of likelihood. So what you can do is you do beam search, which means you basically randomly explore the top k branches, then you go down and you only store your best candidates. And that way you sort of optimize over the likelihood over a sequence and not individual tokens. Uh, and the log likelihood is just a measure of how likely the sequence is. It's just the sum. So if the probabilities are p is equal to the e of, I don't know, the logit or something, then the log likelihood is just the L here. And then for a sequence, that means, so this is the likelihood. So it's like E sigma L, and then the log likelihood is just sigma L.
So yeah, with the beam search, because you can output like 50, like the top 50 guesses, it's a lot more likely will be accurate. And then finally, to evaluate, they just plug it into a computational solver to see if their solution works. And then again, if one solution within their final, like say 50 outputs is valid, then we say the whole iteration is accurate. Okay, so here are the results. Wow, it's really small. But basically we see that it's successful for a model trained on various combinations of each data set. It's generally successful across I guess all 5 of these train and test sets. It performs the worst for ordinary differential equations, but with degree 2, but it seems like this works pretty well. Okay, and then even with only training on the forward data set, which relies on SymPy, which has a lot of capacity to be inaccurate, like say it can't integrate something that is integratable, it still manages to generalize to situations where SymPy can't solve them. And we can see that here where it has like, a non-insignificant amount of accuracy. So that's pretty cool, generalizes. And then here's comparison to the conventional computational tools. Okay, I'm gonna run through this last part really quickly because I don't fully understand it, and also I'm running out of time. So this is basically applying the same technique to an open math problem called Lyapunov functions. Basically, Lyapunov functions relate to dynamical systems. So dynamical systems are functions that satisfy a set of conditions, but mainly they're basically functions that can describe phenomenon over time. And then a Lyapunov function is one that satisfies these 5 conditions. And the main reason why we care about them is that if a Lyapunov function exists, then a dynamical system has a stable equilibrium point. And you can go into the paper and textbooks to fully understand what that means. But this is like really valuable for people worried about dynamical systems, which could be like, people worrying about, I guess like what people using control theory or something in physics. Yeah. So the main thing is this is a cool open problem. Right now there's no real system to discover Lyapunov functions. One way is to use SAS tools, which uses a sum of squares computational approach in MATLAB. And this works for dynamical systems that have that are only polynomials of small degree. So what if we use transformers to discover Lyapunov systems, since we can encode them as sequences? Like maybe we can, discover and then build a model that actually tries to find the Lyapunov function based on a given system. Okay, so we apply the same idea of data set generation. So we can see that like the forward type of approach doesn't work because when we generate a random dynamical system, there's no current way to generate a Lyapunov function corresponding to it, right? So instead, we can generate the Lyapunov function itself and then generate the system that works with it. And there's a series of heuristics to follow when generating in this way, such that you don't allow like the transformer to identify like common patterns. So for instance, if you always generalize or always generate polynomials that are like already factored, then it'll just read the factorization rather than learn how to, work with polynomials. Or in the further case, because this is the actual process, if you generate orthogonal vectors using the Gram-Schmidt process, then it can find that pattern pretty easily. and it won't work very well. So in this case, we generate 300,000 examples, pairs of Lyapunov systems and dynamical systems, which is like a huge amount of discovery, I guess. But yeah. So for polynomial systems, the forward approach actually does exist because SOS works. So this is like a good way to benchmark, but it's very time expensive. As you can see, SOS takes over like 2,000 seconds to generate a Lyapunov system sometimes, especially for larger degrees. Okay, so this is a discussion of like, is this actually discovery? So since like based on the generation scheme, it seems like they can generate like an infinite number of Lyapunov equations because they like just based on their scheme of like backward generation. So I'm sure that doesn't generate all possible Lyapunov functions, and it's not like a method to find like the Lyapunov function for your dynamical system that you're working with. But yeah, that's pretty interesting. And then I was wondering like, why even apply machine learning to this? And I think maybe if your machine learning model can like, properly predict the correct Lyapunov function given a dynamical system, you can, I guess, use that as a verification that these two are actually like correspond to each other and it's valid. So it's like a way to maybe conservatively estimate the amount of systems you can generate with this, but I don't know. What do you guys think? Right? It could be. I'm not certain. A mathematician would know better. Okay, so evaluation again, beam search. It's the same procedure. They use also early stopping, and then they evaluate on 3 different sets. So they have a small polynomial set, a large polynomial set, and then a non-polynomial set. So in their experiments, they have trainings. Well, they train models that are use combinations of all 3, or just train on one of them, and then they look at the results and see that with conventional tools, pretty unsuccessful. Only sauce tools works decent on small polynomials, but with their transformer, oh my God. Wow, accuracy across the board, right? And I think the really cool part is that even when you train on like out of domain, like if you train on only non-polynomial data set, it still learns somewhat. It still generalizes somewhat to training on or to the polynomial cases. So that's really cool. And then okay, and then just to briefly summarize, so yeah, I just want to introduce like a really cool data set generation method, and using that in addition to transformers for math seems really promising, and it's like a pretty novel idea. Yeah. Any questions? Sorry for speeding through at the end. All right. This.
No, it's a non-attendance.
Oh, it's not.
Yeah, non-attendance. So we're gonna be making a newsletter that I'm setting up this week. So yeah, I'll send something to you guys in the inboxes for next meeting.
Okay.
Okay, so the actual attendance, the actual attendance is an 8 piece. So being one of those players can do that.
Also, if you put your name in, it'll help us get more people in the next time. We want to maximize our pizza
Leverages.
Yeah. If I had more time, I would like try to. Oh, it doesn't. So I said I would do demo code, but I didn't end up doing any demo code. Uh,
Solve an equation on the phone. Oh, yeah,
but okay. So this second part is like really, I feel like it's possible to do. So like, yeah, if anyone wants to verify this, the second part, it's like a very doable thing. And yeah, I was gonna do it, but maybe you guys will. Yeah. What's up?
How much computational power would it take to do this? Because the number of like, sort of like these data sets in order to keep clocks described is like enormous.
Yeah, it is. It is quite. So, a transformer has like a complexity of like O of n squared, something like that. Maybe like times some other constants. But so they're very, I guess, like slow algorithms. But if we train them on like GPUs, since we can parallelize like all these matrix computations, it can be done. Maybe on Google Colab, but yeah, I don't know. I've never tried. What's up?
What's that?
Oh yeah, so that's back. So I could explain this a little better, but yeah. So basically, instead of them just having a regular transformer, they add a um, recurrence like structure, I guess, so that each block, like each like say the encoder or decoder, you can recur through it, and it'll track like its current state. Um, like it's denoted like I think HT or something, and then it'll learn like how many times to pass through it to optimize its objective of like for the encoder it'd be like I guess predicting most accurately. But yeah, it's just a way so that because normally how transformers work is you have to pass through each block like a set number of times, and you could determine that by like encoding a number of blocks, right? So say I had like 6 encoders and then 8 decoders. It would be I would have to pass through all 6 every single time I train. Whereas this way, you can for each token pass through the encoder and decoder like a different number of times, depending on how ambiguous that token might be. Also, it apparently enables it to be a universal Turing machine, but that's not what I was focused on. Yeah. Does that clarify?
Yeah.
Yeah, I guess in that case, you guys are good to go.
Yeah. Thanks for coming.